live again.
Hi. Immediately, who is there?
11. We're just testing. So suddenly this works.
360 cam.
360 cam. Yeah.
Okay, you win. I lose.
Oh, what's his name? He said.
Jennifer, அப்படி ஒரு invite அனுப்பிச்சிருங்க.
Dilbert, but Dilbert.
Hello, welcome. Come.
Welcome back. How are you? Happy New Year.
From ticket groups.
So he has to join. So,
Okay.
அப்புறம் நம்ம
See, நீங்க easy join பண்ணிட்டீங்க நினைக்கிறேன்.
Karthik.
இந்த வாரம் தான்.
Okay. So you're from
TCS.
Okay, where? Nice. Sirseri. Okay. Ram.
You are the one who is working.
No. He's yet to come out of college.
I go to college near your office.
AstraZeneca. AstraZeneca.
Oh, okay.
Neville.
You're from Chennai.
No. That was okay. You have seen me some
11th floor. AstraZeneca.
I'm from
Axel. Okay. So where do you work?
It's a ticket group.
Not. Last time I forgot to unmute. I can have the session. Yes. Sure.
Can take any seat. No, I mean we will give a paper probably in the middle. We can just write it. Choose your life.
Just very secure. Let's have the camera.
We should mute for a while and then unmute it. Should we? Yeah.
Today is a very special day for Chennai DevOps Meetup because it's our first anniversary. Unfortunately, we didn't get a buy a cake for it. Yeah. Maybe next time we can. But also very special because we're partnering with the Explosion Meetup as well together. So Karan is the Lakshmi is the organizing committee. And Karan is on the website. He's from Bangalore. So let's start with the introduction first, then we'll catch up with the agenda. Should we have the agenda for the day?
Yeah, it should be there in the site actually.
Okay, we should quick overview of the agenda.
I should have. Paper.
Yeah, Karan is not here, so he will. Right. First one is just tangible fund. Lakshmi was there. Next is Suchi or Suchi?
Sushi.
Sushi. Not sushi.
No, not sushi. No, it's not food.
Yeah. Ashwath is from Index. He is one of the organized for the DevOps Meetup. He is like DevOps, German, there, you know where he is.
Thank you.
Right, we will talk about his current role. Next one we have Shahid. Masura, and talk about his DevOps Meetup platform. And then it's open topic. Right. Actually, I want to use about the platform, the DigitalOcean platform. Yeah, I think everybody knows about DigitalOcean platform. By the way, I don't work for DigitalOcean, contrary to popular misconceptions. So they are organizing meetups in a lot of cities. So this is the first one happening in Chennai, and they expect us to continue the same DigitalOcean space in the upcoming meetups as well. It should be monthly, but we can have it otherwise as well if you guys are willing. Anything specific? Any questions you guys have? I think Karan will be covering more when he comes eventually. We are expecting him in another 20 minutes.
What is the idea of the DigitalOcean?
They just want to connect with developers and then be in the thick of things. They want to understand what people are actually, because we are eventually in one way or the other consumers of cloud, right? They just want to network with people who are the potential consumers. A lot of DigitalOcean partners coming in here today who are in Chennai. That's what Karan told me. So anything under the sun you want to talk about, you can talk. I'm going to quickly introduce ourselves, like a few seconds.
Okay. I'm Mayappan, coming from Rise and Data Service in your party.
I'm Satish. I'm a DevOps engineer in Aeronautics. So having almost 10 years of experience with
Hey, one of the freelancer in Microsoft Technology.
So this is Java guy working for TicketGoes as a team lead.
So myself, Sadhguru, so I'm working as an Android developer in Cover.
Myself, Vijay, working as a Linux admin in Service.
Myself Srini, business.com.
Prasanna, I'm UX designer in Business Kit.
Hari, networks heads here.
Okay. My name is Ramu, working for CPS, Cloud Operations Manager.
I'm Sam Dev, founder of the Ads Meetup.
I'm Ram Kumar from AstraZeneca. I work with DevOps here.
Jay Kumar, working with AstraZeneca, part of application development.
Hi, I'm Ashwant. I work at Index as a software engineer.
I'm Lakshmi Aswan. Like I said, I don't work at DigitalOcean. I work at Axel and I'm a full stack developer. I'm just volunteering for me.
I'm Mohan. I'm a hobbyist programmer. I'm the organizer for Docker Meetup and Golang Meetup in Chennai. And I've been using Go for the past 2 years or something. Most of the time I spend writing some fun stuff.
He's a college student, right? Just in case you're
Hi, I'm Arvind. I'm a founder of startup called Marriage. Everything tech.
So hi, this is Rangarajan here. I am working in Eastern as a DevOps engineer.
Hi, I'm Rajesh. I'm working for AstraZeneca. I'm taking care of the platform team.
Hi, I am Sundar Raman, working for AstraZeneca, enthusiastic about technology.
Hi, it's Kanan, working as a sysadmin in Java.
Hi, this is Venki Selvan, working in Verizon Data Services as a developer.
Hi, I am Adish. I'm working as a PHP developer at Precision Infinite Ventures.
Hi, SN here. I work as DevOps with Higher Exact.
Hello, this is Karthik. I work for TCS. I come from Sirisiri. I work as a project manager.
Hello guys, this is Karthik. I work at Asana as an application engineer.
I'm Shahid, I'm a platform engineer.
Hi, I'm Praveen, I'm an application engineer.
Hi, this is Ganesh. I'm working as a PHP developer in TCS.
Hi, this is Ramesh from Kotak Markets, working as a technical consultant. Hi, this is Gaurav from Kotak.
Hi, this is Dinesh. I am working at Car Technologies as a technical consultant.
Welcome again, everyone. I'll quickly do a highlights of what our meetup for last year. We, as of I think January 1st week, we had 456 members in our DevOps meetup group. And we had 11 meetups. One after we had to cancel because of the rain around the mid, I think it was March or May. Presentation from non-AstraZeneca employees and 5 from AZ employees as well. And we had 2 presentations from overseas. One of them from one of my friend from Red Hat is in Brisbane. Another one from our CTO team in San Francisco. And started recording the sessions in YouTube and making it available on the channel as well. That's it. Let's start with the first one. Guys, who want to go first?
Okay, I'll go first.
Go first. You want a mic or you want happy to?
I'm happy to speak.
I heard the audio is pretty good with the mic.
I'm gonna assume I didn't hear that. Okay.
Sure.
Instead of helping. Ashwat, what's your email? Got it. You are the topmost Ashwant in the world.
Probably the oldest Ashwin.
When you join, okay, well, Ashwin, share from here. Once you join that, yeah, I can make you as a present.
Would it be in sync?
Yes.
Yeah.
Video. Good. All right. I'll make you as a presenter so it will record. Yep.
Let's do a full screen if you don't mind. Awesome. Hi, can everybody hear me?
Yes.
It's customary that we ask this question. Okay, so my name is Ashwant. I work as a principal engineer at Index. That's my Twitter handle. And I'm going to talk today about one of my open source libraries that I've been working on for the last couple of months called Sochi. It's a toolkit for building application layer sharding. It can also be used for building distributed data stores and things like that. I know some of these are fancy buzzwords. Hopefully, I'll be able to convince you this tool does more than talk about it. Okay, so And the general thing, one of the things I really follow when I talk is, if you guys have any questions, just stop me and ask me. It's better if we can clear those questions with the context of the slide and in the flow, so that I'm happy that I'm able to communicate the message across to you, and you're also happy that you get what I'm talking. I'm not very fast, right? The space is okay.
Yes.
Awesome. Okay, so we don't get to talk about distributed systems without actually trying to understand how systems actually scaled over time. So the following few screens are going to be a very opinionated view of how I think the system scaled from, especially in the web world, from say early 90s or mid 90s to what we have today. What things started as a very simple systems to unmanageable beasts as we have. So this is probably how systems used to work. So you used to have users, any particular website, which would typically talk to a database behind the scenes and give you back results. Very simple architecture. This is what, unfortunately, people still teach you at colleges. I mean, this is what even I was taught to when I was in college. And it was all cakewalk. It was very easy. When I built systems like these, I was like, yes, I figured out how to do software engineering. I'm going to be very successful for my career. Only to realize when I came back, this is a reality which was like probably a few decades old. What happened is, people in the early days, we started having more users. And as we scaled more, we started saying, you know what, my service is that single box. Hello box is not able to handle the load. So I'm going to add more hello boxes. Now, with more hello boxes, you started having more users. And this cycle just went on. It was in a catch-up phase, one like scaling for the other scaling for the other. At a point where we started realizing services can scale probably because they are stateless. By stateless, what I mean is we push all the state to another system, which is probably a single threaded or a single source of truth, and that gives you asset guarantees, and that guy can really scale well. But and in the process, we made these guys stateless. To put a load balancer on the top and handle the request as and when they come. After a point, people started realizing that one small white box that you have in the bottom starts to become the bottleneck of your entire system. Generally, I mean, in my experience, most of the cases when you have issues with scaling, it's probably in this layer. Not because the system is insufficient, but more because we have queries that are not very optimized. Probably we haven't set up indices for some of the columns on or some of the tables that we are trying to access to. That starts to come and bite us after a point in time, say a few years or a few months after you start a startup, start your company or a product, and then it really launches or it takes off really well, and a lot of users are trying to access it. This guy goes down, and the entire service now becomes useless. Right? And what people did in the process is, you know what, I'm just going to shard my databases also, which was what was probably a thing when I was at college in 2008-9ish. This was a thing where you start having these clustered databases instances, and that was the approach that even Facebook took, where they made a lot of changes to their MySQL, and they started having MySQL clusters, which scaled really well. To a point where you start realizing keeping these, see, unlike services, these are all stateful systems. When you have state in the process, it's a very, very hard problem to keep them in sync. By sync, I mean, okay, this service is writing, say, an insert here. How do you make sure when this service is trying to access it gets the same copy of the data, right? What sort of consistency guarantees does your application give, or the application proposes to the end users? All those problems come into picture. And what we started doing was we started changing how we access the data or our data stores itself. It started, it started way before, but one of the really good breakthrough happened when Google published its big table paper back in 2006, where they said it's basically a key value store, or it's more of a columnar store, where it's distributed, it's replicated, and it's fault tolerant. It's a system they built on top of their GFS. It's called a Google file system, which by itself is replicated and distributed. And the guy is like a Bigtable is a huge hash map, a sorted hash map. That too, it's sorted based on the key. If you guys are familiar with Java, it's basically a tree map that runs on a huge cluster of machines and gives you access to a particular key. And they said all the earlier asset guarantees that we are used to when we were in the Oracle, Postgres, and MySQL world, all of them went out the door. And they said, we give you consistency guarantees only through for a given key. And now you have to change your entire application's access pattern to data to be on a key based, rather than like, it was so easy for us to just do a select star from something or a select min of something, min of star, a count of star and all that. All those aggregations went like this, so stores couldn't do any of those things. Pretty soon it was followed by another next year. It was Amazon released a paper called Dynamo, which like a few years back became a commodity product by itself. And there were a lot of forks out of the Dynamo paper. One was Cassandra, it was a year later, and then you had Waldemar DB, and then you have React, and all those bunch of systems started in the ecosystem, trying to handle the constraints of the cap theorem, either to say I'm going to compromise C, giving you more A, or I'm going to compromise A to give you more C. Okay, so you folks understand a cap theorem? No. Okay. So cap theorem is basically like a rectangle where it says you have consistency, availability, and partition tolerance. So what it says is when you have a cluster of machines in a, say, in a distributed fashion, network partitions are bound to happen. There was one person who works at networks. It was you, right? So someday you just happen to stumble upon a rack in your Ethernet, the RJ45 cable. It's RJ45. It just gets cut off of the rack, and then suddenly your entire rack doesn't have network access anymore. And the data that was there on this machine and your is not available to the rest of the clusters that are out there on different racks or on different data centers. And sometimes you have which the system will detect it as a failure of these nodes. Now, these are what we call as network partitions. It could be because of a wrong routing table configuration, or somebody just tripping over a cable, or somebody just accidentally cutting a cable, or you lose the power to the entire rack. Network partitions happen for our data stores or for these stateful systems. How do you make sure you give consistency guarantees when they try to access the data, or do you give availability guarantees? Like, is my system available even on case of a partition, when even in case of a network partition, or does it follow, or does it tilt towards consistency? There was this huge, pretty awesome scientist called Brewer. It's called Brewer's conjecture. Cap theorem. He says that when a network partition happens, you can only choose a consistency or availability. You can't have both. And by that, what he means is you can either build a system that tilts towards consistency by giving you a consistent results, availability. That is, there are a set of say records which are there on a shard that just went down in a partition. That system won't be able to give you access to those records, because if I don't know if they are there within my reach, I can't give you consistency guarantees. What the other guy says is, where I don't try to be consistent all the time, but I make sure you are able to access the data at any point in time as and when they come across, as and when they're available. So they give you more availability rather than giving you consistency. And they handle consistency through a lot of various techniques. We'll probably discuss it in the end if you have more time. So Bigtable was more of a CP system where it gives you consistency on the event of a partition tolerance. Dynamo, Cassandra, Waldemar are all AP systems where they give you availability in case of partition. This timeline is by no means it's complete. It's probably 7 years old, 6 years old, and the lineage goes on like this. So what we ended up doing when you pick one of these systems, say the HBases or the fancy MongoDBs or Reacts or Cassandras, you replace your individual sharded databases by one system. Even though we know Cassandra runs in like bunch of nodes, we don't see them as 4 different nodes. We see them as Cassandra as one single point of system, which I talk to store my data, whatever queries I want to do. And over time, people started realizing the system is also not scaling very well because there is this inherent network latency. Now, these cases are specialized data stores, but still running on separate set of machines or hardwares or nodes, if I have to put it that way. And your services still run on separate set of either on different nodes. They don't run allocated together. costs you have to pay. Okay, that's actually network latency, and I think it's getting chopped off. But yeah, so that is this inherent network latency that you end up paying when you're trying to access data over the wire. And what people started realizing in the process is, because what people started realizing is you need to co-locate the data along with the services in order to improve the performance. Why did that happen? Because there was this huge thing for data locality based applications. That is, when you want to serve certain kinds of requests or services, you want access to the data co-located within the service, so that you respond, your latency is very, very small. That is, you respond to it in like sub-milliseconds or a few milliseconds, in tens of milliseconds or even less, rather than having hundreds of thousands of milliseconds, right? And these are very common in data-intensive applications.
Ashok, could you give an example just for better understanding?
Okay, so data locality can be viewed in two ways. One is, take for example the Google Translate system, right? You have these translation models that they have built, and they typically co-locate that along with the service that actually responds to your translation request. So that though it's sort of a read-only system or a store, but you still co-locate the data along with your service so that you can respond to your users much faster. Imagine if this is available separately in another set of systems, and for every request that comes in your front end acts just as a proxy to proxy the request and get it back and respond it back. There's a huge amount of multiple hops you make in the process that turns out to be very costly, especially for these online systems, these user-facing systems, right? And the other cases is, for example, when you have these IMs, right? When you know you're talking to a very close set of people, you would have your co-located to your servers, either on the same machines or something within the same subnet, so that they have faster access to the caches, and then you can eventually converge this data, like either through background jobs or periodically get the data and merge it with the rest of the store for historical purposes. So those are kind of the places where you have data locality is absolutely necessary, because you have this requirement of low latency, and your data is also pretty high that it's costly to send data over the wire to all the machines or to your cluster or sharded systems to get the response back.
So if you just drill a little deeper in terms of the actual implementation, so we understand there's the application service, then there's the data store. So how would you actually implement that? Would you move a transient data to your application service?
Correct. So what people have started doing is you started having these embedded data stores coming. One of the examples I can give you is Facebook's RocksDB, Google's LevelDB. So both of them follow a very similar architecture to what Bigtable has. It's sort of columnar, you have multiple column families, and it gives you a key value access. What these guys did is they started having, and RocksDB, though it's a key value database or a data store, it's not a system. It's not something that it runs, listens to a TCP socket or a connection and then responds to requests. It's a library. It's written in C++ that you embed into your application and runs within the same user space of your application. So whenever your application crashes, this data store becomes useless. It doesn't run. Whenever your application runs, it comes back up automatically, and it launches its own set of threads and manages its own life cycle of what it needs to do. That's sort of how people are going towards, and those are some of the things you use. And this is also very similar to, I mean, it's equivalent to having, say, a Redis or some other things running within the same host. Them over a port or something, to talk to them over a Unix socket. So that you don't go through all the 7 layers, but you just try to quickly bypass from the third or the third layer and then directly go to the other application to respond. This is like that much amount of hops lesser, improved latency. Okay, so this is what people started doing. We talked about it, and in process, what we realized is, the other part is you shard these data stores into individual chunks, and then you had a system in place on the top which can route requests to the right instances based on a particular key or a particular request ID and whatever. What we did in the process is we moved all the complexity that the distributed data stores handled all the way to the application layer. Now, all the problems of consistency, all the problems of availability, I mean, you're still bound by the law of CAP theorem. constraints are now you basically brought it up to your layer of application. Something that you took for granted earlier, because for the cost that you want for performance, you started now paying that cost here. And there are a lot of ways you can handle this. And we had a bunch of requirements at our organization to solve some of these problems. And that's when we built this toolkit called Suchi. So Suchi is basically a bunch of things given to you. They give you a transport layer. By transport, you mean you need some kind of a messaging paradigm or a messaging infrastructure to send requests to other nodes in your system or in your cluster to get responses back, or you need some some kind of a transport to do replication and all those kind of things, right? So Suchi gives you a layer that can handle the transport for you. It also gives you what is called as membership. So by membership, what it means is you need to know there are 5 nodes in your. When you're talking about a distributed system, you need to know who are all the participants in your distributed system. You either there are multiple ways you can do this. You generally have a master to whom everybody registers, and then your master becomes a source of truth. And you have started having. You would generally have, an active master or an active passive master. Somebody who will be on a standby whenever this guy goes down. The other master will come back up to handle your request. That's how Bigtable, HBase, those kind of systems work. When you come to the other side in say Cassandra, Dynamo, all these AP systems, they don't have a single point of failure. When you have a master-slave architecture, your master inherently becomes a single point of failure. But when you have these peer-to-peer systems, every peer is there is no difference from a node 1 versus another node 2 who's participating in your distributed system. So this guy handles the membership. Okay, how do I know a new member has joined? How do I know a member has actually gone down? How do I know when, say, he's flapping? By flapping, what it means is somebody is coming up, for some reason he's going back down, for some reason he's coming back up. It could be a network disturbance, it could be application continuously getting restarted because of some loop or something, right? Those kind of things. The other one is basically the routing strategy. Now, this is some of the very fundamental thing, because when a request comes, let's say in a case of an AP system where anybody could be, where everybody is equal, you can send your request to anybody in your system. Now, when you do that, that person should know that I'm not someone who can handle this request. I need to forward this request to somebody else who's the right person to handle it. Right? Now, in a master-slave architecture, your master is the source of truth. He can do all this logic, and you would have all the information to do it. In a peer-to-peer system, how do you do that? Right? You need some kind of a mechanism to do it, and Suchi gives you that as
like a load balancer, like load balancer.
Balancer is probably not the right way to say, but it's something very similar. I mean, in load balancer, it assumes everybody is equal, so you can it's not necessarily, but most of the time when you talk about load balancer, you assume all the persons are equal, and you can route requests to anybody using some algorithms, either using least connections or based on the custom metrics, system metrics you get from them. You can choose to route the requests. But in here, only certain members can access it. You can't route that request to everybody because you have sharded it. If you're in your entire key space, there is only, say, this segment or this arc in your total key space is managed by this machine. If your request falls under this arc value, only this machine or this data, wherever it's replicated, only those machines can handle it, and not everybody else. That's the difference.
Like a registry in that to register certain systems do that particular type of work.
Yes. So it's like a statically assigning load balancers. Whenever this guy comes, to give you an analogy, you have used HA proxy. In case of HA proxies, you have these multiple front ends, right? You can have any number of front ends, but typically HA proxy is always one process that runs, that listens on all these different ports for connections. It knows it has a static mapping that says whom to route the request to, and from the front end, it goes to the list of backends using the load balancing algorithms. Now, this is something very similar to that. You know, when it comes on this port number, only this front end can access it. I can't forward the request of front end 1 to a front end 2 or 3 because those applications would not even understand the request that I'm sending. That's what this guy does. So she does this. It gives you all these 3 things as a tested pluggable library. Okay, so you just focus on writing the business logic, what it needs to do, and this guy provides you all these facilities to build and use your system. Now, This is not.
Isn't Suchi similar to master slave architecture?
No, that's something that's an implementation detail. That Suchi does not make any assumptions of what kind of system you're building. The current version that we have, okay, that's actually github.com, my name, and it's available in this repo. It's open source. Now, what that guy does is the current implementation, the master assumes you build a peer-to-peer system and not a master-slave system. But there is nothing stopping you from building a master-slave system to do it. So the way it does membership management is through you need a consensus protocol or a consensus algorithm in place. Generally people use Paxos, implementation of it as Zookeeper, but we use Raft for managing our membership. And for routing strategy, we use consistent hashing, very similar to what Cassandra uses underneath it in React. And for transport, we use HTTP2 because that supports bidirectional streaming across secure connections. We'll walk into each of these now. So far, you guys understand what was the need for building something like Suchi?
The topmost question, business logic, it deals with our application business logic.
Yes.
Or
application wants to build. The other thing, I'm just trying to explain Suchi in a more fancy way. To explain it in another terms of what in the current trend is, this is a library that can help you build microservices. Right? That's another way you can also think about the same thing, where you have stateful microservices who needs to understand what is the state between these two, or where to route the request based on the incoming request that comes in. Those kind of things can be built using Suchi. And this is currently written in Scala. Oh, sorry.
Yeah, can you say that you're pushing the problem one layer up?
We talked about this one. You mean this one?
Yeah. Still dealing with that at the data storage level.
It's about latency, right? Latency between that hop.
Your application and your data storage.
That still happens in the application layer as well.
Correct, but the reason is if you can route requests to the right service, the service response time is much smaller.
You're bypassing several layers.
Yes.
Okay.
That's the only drawback, right? So we are at a point where we're trying to push ourselves to as much as we can to gain that 5 millisecond or 10 milliseconds gain in the response time, which can have drastic impact when you have a large number of users using your application. That's the.
So is it not similar to in-memory database like what we talked about? Is it closer to that?
It is, but the in-memory databases would still follow, this kind of an. This guy, instead of storing data on disk, might store it in memory, backed by disk. But the access to your data stores would still be over the wire. Unless you say I'm using a data store library that can handle distribution, that can handle sharding, that can handle replication, and still hold the data in memory and give me the performance. Anything is like that already. Then yes, it's the same as what Suchi is trying to solve.
So you're sharding at the in-memory level, something like that.
Yes, the entire data, right? So maybe I'll walk you through how the sharding happens. That way I'll be able to explain more with pictorial representations. Can we proceed?
yes.
Yeah, so this is what sort of Suchi gives you, and as I was saying, this is written in Scala, so it runs on JVM. So any JVM language can use Suchi. We'll also see. The last slide, one of my last slides is Suchi is not something new, and there are also implementations very similar to Suchi available on multiple languages. If you are not a JVM person, you can check out that as well. Okay, so the transport. So for transport, we use something called as gRPC. Basically an RPC library or a framework from Google. Very similar to if you have used Thrift, you have an equivalent system from Twitter called Finagle that operates based out of Future and over the Thrift transport. And this is from Google, which sends protobuf or protocol messages over the wire, and they use HTTP2 transport for doing it. And the reason is the reason why this is something better than just sending JSON messages or requests over the wire through a normal HTTP 1.1 or 1 is this guy supports streaming. If you're familiar with HTTP2, you sort of understand the benefits of it. So you can multiplex requests in a single connection. Not one or one. In HTTP 1, it's completely stateless. In HTTP 1.1, you still have a notion called as pipelining, but pipelining is still sort of sequentialized. You can send requests at any time, but the server still has to sequence those requests and give you back in the same order in which you send the requests, right? That's what pipelining does. That was one of the features of 1.1. And come HTTP 2, you have streaming, like first-class streaming support. You have what called as a BD streaming, that is bidirectional streaming. You can send requests over the wire to another guy to the server, and he can send back response in the same channel. And they can be out of order as well. I mean, out of order means that one request can be blocked by the other. The package is still ordered because that's guaranteed by the TCP. Okay, so we use gRPC for that particular reason. And for membership, we have two ways. One is basically a static membership. That's what is currently running in our production systems at Index. By that we mean have a plan to scale up instances dynamically as and when it grows, because we have large amounts of data system that's using Sushi. So we have a static membership where we say these are the 10 nodes, and this 10 nodes shall remain the same way. Now, the drawback with that approach is if you want to scale add a new server, or you want to remove a new server, it needs restarting of processes. You have to push the configuration, restart all those mechanisms. The other one is basically the dynamic membership, which is what these Cassandra, these big table kind of systems gives you. This is where you use a notion of membership, because this is where the membership is really needed. And they are fault tolerance in case of node or a process failure. Let's say if a process crashes because of some out of memory or some other reason, you can always, like, if you can have a monitor in place which would restart the process and things would just resume from that point.
Any election will happen. Any node get failed at the time election will happen.
Leadership election.
Leader election. Now, leader election is a matter of if you need a notion of a leader, right? So in a peer-to-peer system, you don't need a notion of a leader. That is the case on systems that are built like this. The reason you would need a leader election is if the leader is supposed to be the source of truth of a bunch of information. Typically, it's the metadata that says who are all the nodes in the participants in my cluster. Where are they listening to? What are some of the metrics? If you have stateful single source of truth, then you need a leader who needs to hold that information. This is typically what in your master-slave architecture you have. But when you have in a peer-to-peer system, you generally don't need a leader election, because you don't need to elect a leader because everybody is the same. That's democracy done in a different way. Rest routing, we talked about the net layer. So we use what is called as consistent hashing. So this is the paper, if you're interested. It's called Consistent Hashing in Random Trees. Was published by an MIT professor back in 1997. This was initially built proposed as a way to, as a load balancing algorithm to relieve some of the hotspots when you're routing requests. But later, a lot of systems started adopting the CH ring for doing sharding because it naturally fits into that space. So what it does is, I'm just going to give you a very high overview of what CH ring is. By CH ring, I mean consistent hash ring. You're wondering what CH ring is. So let's say you have these 4 nodes. You use an hashing function. Are you guys familiar with MD5? So can anybody tell me what is the output range of MD5? What is MD5? Whatever be the input, what does it give you back as an output?
So it's a dealing about eventual consistency.
No, MD5, not talking about CH. Yes, so there is a fixed length to it. So MD5 gives you a 128-bit hash output. It's basically an alphanumeric value, and it always, if you see it, it'll be 32 characters in length or 128 bits. That's like a fixed size thing. If you go with, say, something like SHA-1, for example, I guess it's 160-bit output length. So it sort of depends on different hashing functions have different. And if you take any hash function, you plot them in a graph, or say, what are the possible set of values that you can get out of this hash function? What you would end up with is basically from 000, that is your bit alignment. Like say if you're taking MD5, it's like, I'm I'm very sorry, I can't see you guys. It's totally dark. Please. Okay. So you have these 128 bits. So we have 128 zeros. Every bit changes. You just change one bit at a time, 0 to 1s, and then that's how binary operation works. And the last or the final value would be 11111. Right? That's basically a range. You change one element, one bit at a time from 0 to 1 and alternate between zeros and ones. You get a huge truth table for all these 128 bits. That's like 2 power 128 combinations, and all those 2 power 128 combinations can be plotted in a circle.
No, nothing happened.
Your slides are better now.
And it's colorful, it went on at the right time.
Okay, so if you plot them in a circle, right, they will actually, the total space can be drawn as a circle. Each of these points represent a node positions. Now, how we do that is we take the node, let's say if it's node 1, and we say how many times you want the node to repeat in your total key space. Let's say in this case it's 3 times, and you say node 1:1, and then you apply the hash function. It will give you back an output. You plot that here, it will be the first node. If you take node 1:2, it will come here, it will come sometimes here. I mean, these are just representations. The real position might vary. But the beautiful thing about the certain classes of hash function is it gives you an equal distribution of the hash output if your input is equally distributed. It sort of gives you that. But it also has some of the problems, and that's why people at Cassandra have moved from MD5 to Murmur-3. And SHA-1 also gives you something very similar. So when you have these equal distribution for the given input, if the output hashes are also equally distributed, we can sort of plot them and it will come something like this, right? And what happens is, when say node 1 goes down, it's sort of marked as something that's down. What happens is all the data, okay, this is something I forgot to tell you. When you have these rings, when you have these dots in the ring, any request, you would hash that request also using the same hashing function. Now that request would fall under again somewhere within that range. Let's say if it falls here. What we say is any request that falls from the previous ping to this red would be handled by red. You can either go in clockwise or anti-clockwise. It's a matter of preference, but you always choose one and be consistent with that. So any request that falls under this range goes to red. Any request that falls under this range goes to green. Now, let's say when the node 1 goes down, all the data this guy had from this range to this range would now be transferred to this.
Yes.
So now after, let's say it happens with all the individual instances, you have all these shards. When that happens, this is how the ring will look. So any request that comes within this range to this range would come under here. Now this guy, because he had the data, would be able to do it. Now the initial version of the paper does not talk about having multiple instances of nodes. Sorry, sir.
Including session replication when the payload happens.
Session is basically another form of data, right? Something you have a key and some value, say in forms of cookies or some metadata in a JSON that you hold in your session store, where you have a pointed access to. Now, when this guy fails, he would transfer all the data to here, and
including session,
including every data, not just the request sharing, it's also the data, so that this guy would now be able to handle it. Now,
so when that guy is going down, what ensures that all the data is being transferred before it is removed from the link?
Right. So there isn't any. That's the beautiful thing of it, right? So in case of a process failure, probably you can have another watch process, a watchdog kind of a thing, which can push the data across, goes down. As the cases when we talk, somebody tripped over the network, and your network, it's as good as somebody terminating your droplets. I said droplets. Somebody terminating your droplets on the your DO account. It's like you lose the data, right? If it's stored on ephemeral disk. Now, when we had, this was the initial the representation, right? When the request comes here, we said it will be routed here. Now, imagine if you have to implement replication, how would you do it? The next guy who comes in the ring, who is not the same node as me, get data. So this node, the original data would be stored here, the replication would be stored here. So when this guy goes down, naturally the replicas would take over.
So that means we have a constant gossip between the nodes.
Yes, so it depends on how the replication is also implemented, right? What she does is it doesn't deal with consistency problems, or we just didn't want to deal with it right now. So we said we will support only synchronous replication. That is, as part of every write, if you say your replication factor is 2, we will try to replicate it to 2 nodes. If the replication fails, we say the write has failed. So your application, whoever is doing a write, can choose to say if he or she has to retry the request or not.
So the transactionality includes the replication as well.
Yes. So that's because it was very easier to build and also reason about it. There are systems, again, Cassandra supports async replication. But in order to support async replication, they have a bunch of systems and a bunch of techniques in place. They have this notion of hinted handoff, which gives you partial availability for replication even when the other node is down. And then you had a full Merkle trees to identify diffs between the data that is like not there, and then do a sync between the 2 nodes when, say, you bring in a new node completely. They have these lot of mechanics to handle it. We didn't want to enter that realm right now. And most of our use cases, just 1 minute, most of our use cases, synchronous replication seems to be a good trade-off. So we just went ahead.
So essentially at the node level, this is like a master-slave setup.
Master slave, yes, for that particular request, the entry point, if it falls here, this guy would be a master for that single request. In Cassandra, it's called a coordinator node. In this case, you can call it as a master node. He is responsible for replicating it to the next write. If the replication fails, he would say the write has failed. So it's a blocking call until replication completes.
Sequence of node replicates.
Correct. I mean, the thing is, his replication could be stored here, and his replication would be stored here. If you have more than 2 nodes, let's say your replication factor is 2, and you have 2 nodes failure, you have data loss. So your replication factor can only support up to, I think it's n-1/2 failures. So if you have 3 nodes, you need at least a replication factor of, say, some quorum, so that you have majority of the replication still lying around somewhere. If you want to support 2 node failures, you need 3 replication. Basically, how many failures you want plus 1 is the number of replication factors you want. Because it's guaranteed some guy in the node cluster will always have your replica, either the second replica or the third replica, or whatever is the n plus 1. Right? Okay. So we talked about this is how the request routing happens, and replication also happens as part of writes. The things are, it's basically a peer-to-peer system, so there's no single point of contact or failure. You can talk to anybody, and the whole system works as in a handle or forward fashion. That is, each node handles the request if it falls within its realm of the CH ring. If it not, it acts as a proxy to forward the request to anybody else in the node who falls under the same ring, right? And because CH ring is completely let's say you take the static membership approach, CH ring can be built independently on every node. They don't need to have a gossip, or they don't need to have any consensus mechanism, because it is guaranteed to be the same. When each nodes know what are all the when all the nodes that are participating in your whole system, right? And one of the things I really like about Suchi being a software engineer is everything is pluggable. You can take out your replication logic and from a synchronous replication and implement an async replication flow. You can take out CH ring partitioning scheme and implement, say, a renderless hashing partitioning scheme, or a weighted distribution or weighted balancing partitioning scheme. All those different kind of things. The entire system is built as a pluggable module, and you have sensible defaults, which works for most of the times. If you need some configurations or customization, you can always flip that in. So how do you sort of get started is you define a gRPC service using Proto 2 or 3. You generate the stubs, you implement the services, and you connect all of these together using the server abstraction. I'll probably show you some code.
Proxy, what application are you using?
Sorry?
For proxy, you told them proxy we are using. What application are you using for same switching or some other application?
Proxy. I mean forwarding request.
Forwarding.
Suchi does that also. Suchi itself does the forwarding of the request. What I meant as proxy is if let's say I'm your node 1, I'm node 2, and if he's sending a request to me, but the request can only be handled by you, what I would do is I would not say I can't handle the request. Instead, as part of request handling, I would transparently forward the request to you as a client, and you do whatever processing you want. You give me back a response, which I'll forward it back to the actual user who sent me the request. So for that request, I act as a proxy. So same thing works if it's the other way around, right? So that's the idea. Okay. Awesome. So I'll give you. So I'll go into the proto definitions a little later. Is this real? You guys are able to see?
Yeah.
Okay. So forget all these inputs. Maybe what I should do. Skip these guys. So let's say this is your server. You're trying to build a distributed key value store, and the key value is actually say an in-memory store. It could, in this use case, it's basically a concurrent hash map that we have as a key value store. And what you have to do is you have to define how many partitions per node you want, what is the replication factor you want, and then you define a routing strategy. We use a consistent routing strategy, CHRIM. And this whoami's are basically a list of all the nodes that are there. And then you define what is the store, what is their underlying key value store, and then you connect all of these using the servers. The server abstraction, that is, say, have a read service using this routing strategy. And for the write service or the put service, you have a parallel replication using for this many number of replication factor and this routing strategy. Now, essentially, this is all the code you need to build a distributed, replicated key value store. Okay, that's an elevator pitch. So that's sort of how this thing is built and works. And most of the things at first seems like pretty nice because most of it is abstracted away and a lot of things happen behind the scenes. But as engineers, you would, if you're someone like me who doesn't want to use a system, if you don't understand the details, sort of not something that's very pretty. And you can dive deep into each of this code, and we have tried to have enough test coverage. And we're working on integration test for this, but we have unit test coverage for most of these services. And the replication part or the request routing part or the CHRIM building part. I have overshooting time already. Okay, I'm very sorry, I finished it up. So this is sort of a protobuf message definition. It's like this: a get message who takes a get request and a get response. A get request just has a key where you can do a key paste lookup. Your get response though will have both key and a value. Let's say we assume for simplicity, all of them are array of bytes. You deal with key values as array of bytes. And this is how your write service would look like. You have a put message which takes a request and a response. Your request will contain both key and value that you want to put. Response is basically a boolean that says if the request completed, fine. And this is sort of the implementation. So this is what the business logic I was talking about. Supplication, you would code as part of gRPC. You define the get request. The syntax is Scala, but I think you can follow it. So you take the key that you got, and with the store you say store.get of key. If you have the key, which means some says there is a value present for that key, you create a response using the get response method. You set the key, you set the value. If you don't have the key as a value associated with the key, you just say there is nothing. You just set the key and then you say your response is completed. And that's all there is to it. So this is how you implement your business logic. But behind the scenes, she takes care of routing the request to the replicas, handling the replications and all of that. Similarly, yeah, this is the code that I showed you recently to connect all the different services using the server abstraction. Okay, so to answer your question, where are we using this? We have an HTML archive system that's running in production today.
So that system handles more than, currently we have 10 nodes in that system, and each node individually sort of takes somewhere around 300 plus requests per second, writes per second. And the whole system is a write heavy system. So as part of our workflow, we crawl a lot of pages, and as soon as we crawl, this guy starts indexing it. For developers to debug the data if you want, or systems to go relook into what the old data was and run some benchmarks or any processing you want. To give you a size, it has close to 1 year worth of data indexed, and it's around 120 plus terabytes of data with replication. The other couple of systems we are planning to integrate Suchi is one is for the stats storage system. So we don't use our stats storage, so we don't use any of the existing metric system like Influx or Nagios or any of those things. We have our own, which is built on top of monoids, where every stat metric we wanted was either a sum of all the things. Most of them are aggregates. Basically, all of them are aggregates that we wanted. And aggregates can easily be modeled as monoids. And I'm not going to get into what monoid is, but it can be, it's something that's incommutative. If we are talking from strict mathematical perspective, that is, you have two metrics, A and B. You can add A plus B in any way you want. It can either be A plus B or B plus A. It will still yield the same result. Where plus is not the addition, but some operator that you want. And the other one is basically A plus B plus C is same as doing A plus B plus C or A plus B plus C. Any order you sort of apply grouping and apply. That's what associative and commutative means, right? Okay, I'm sorry if, because sometimes when I talked about this, people didn't understand what associative and commutative is. Right? The last one is real-time scheduler. For our crawlers to get pages that it needs to crawl, we have it sort of does it in real time. Scheduling of the URLs. So we have a total corpus of around 3+ billion URLs, out of which for every request you need to pick 20 URLs and return it as a response. It uses a lot of data structures behind the scenes to prioritize those URLs and algorithms behind the scenes, but sharded in such a way that could be sharded in such a way that a site-specific request is replicated across multiple nodes, and that layer is built using Suchi. Yeah, this is the last slide. Just for 2 minutes. So the idea behind Suchi is not something that's new. The fact that you need membership, you need request routing or sharding has been there for quite a while. The first attempt was made by a library called Gizzard from Twitter. It's now sort of dismantled or discontinued, but that sort of lays a very good foundation. It talks about a lot of abstractions in place. The next one, a couple of years back, was Ringpop from Uber. I mean, first time I got to know about this, I just knew Uber as some app company that serves, very similar to what Ola does. But the software engineering tools and problems they solve was really fascinating. You should check out the GitHub profile. Ringpop, which was initially written in Node.js, and then they also had an implementation in Golang, which is exactly what Suchi does, but it's very less opinionated. Suchi is a bit more opinionated than that. Next one was last year we built Suchi, and in November 2016, Google published a paper in VLDB called Slicer, where they built whole sharding as a service, and it takes a lot of lessons or the similarities between what Slicer does in terms of routing, in terms of making sure getting more metrics and having replication is very similar to in just without the data part, just on the service request routing part, it's very similar to what Suchi is doing. So yes, that's a little bit. So I have another GitHub repo which will probably post it on the meetup page. This has all the references to links and YouTube videos that I used to get prepared this presentation. I also have credits to those images and content. Any final questions?
Well, let's say that I have an existing setup which uses SQL or HBase. How do I adapt to this?
I mean, you don't have to do so if there is no need to do so. HBase seems to work fine with the latency and all of that. HBase is far more superior to what Suchi is right now at this point. Unless you find there is, if you are users of HBase, Suchi is not the thing for you. something that is homegrown or you're trying to build something where you're trying to run an embedded database in the same machine or as a library in your application requests in a much faster fashion, then Suchi is something I would recommend you to go try it out. It's not a replacement for Cassandra or HBase. This is something that we had a need for it at Index to build something like this for our use cases, and hence it grew out of that. So that's why it's in a lot of ways it's very opinionated and not that feature rich compared to what some of these existing tools provide.
Major success stories in terms of clientele.
Sorry?
In terms of clientele, implemented it, do you have any major success stories?
This is just us, just me. So I started building this in September, October last year. I was saying, right? There was here, this person was giving a talk in same Chennai DevOps Meetup, I think it's about Cassandra. And then we went into this really huge debate on how the replication works and how the consistency guarantees are maintained in Cassandra. And we all agree to disagree. And that's when I thought, okay, you know what, how hard would it be if I have to build Cassandra from scratch? And that's how this exercise started. And I realized in the process, this is something I could use for some of the problems we were solving, and adopted it for that and built a lot of bells and whistles and some documentation. Invested some time on testing, end-to-end automation. Cool. Thanks, people.
Let's see if I can get the extension on that. Balaji, Karan. Hi, Karan. Karan.
Let's continue, no problem.
Address, please. 1 second, let's just add you. AHADH. HAXIBHDH at hasura.io. Right? Yes. This is join. That's it. Yes, sir.
Want to break for 10 minutes? Break and then start.
Yeah, it's a good idea. We wouldn't like to have a 5-minute, 10 minutes break.
I know I talked a lot. Made you sit for a long time.
Yeah, I think 5 minutes would be good. By the time I'll fix that screen as well. Hello, Karan.
Hi.
Sorry? Was it my time?
It's somewhere. Keep traveling around.
Yeah.
jump into who we are right now. So I'm Shahid. I'm a platform engineer at Kasura. There's Karthik and Praveen there, and they work on application engineering. So let's get into the topic right away. So what I'm going to talk about now is containerized microservices and why would you want to use them, and some pointers on why shouldn't you use them. Like, but certain use cases where it is very useful and maybe certain use cases where it's not useful. The reason we are here discussing and you have been hearing the term the cloud. What is it? So people have been deploying applications and the servers on virtual machines for a long time. But since when did this term so well? Why is everybody talking about it? They will bring in a very basic innovation, which is called VM provisioning, which is lightning fast. So basically, when you need to set up a new machine, service providers like DigitalOcean, you just do it in a couple of minutes. 1 or 2 minutes, you have a new VM. So what you get is a place to host your application as quickly as possible. So earlier days, what you did was, let's say you're expecting some 10,000 users, and you somehow have a rough calculation and said, I might need a system with 8 GB for that. You provision that system initially itself. This is only come on weekends. All the other time, the system is wasting resources. You might be utilizing only 10 or 20%. There may be some 1,000 users coming in. Using these kind of VM provisioning, we can dynamically allocate resources. You can bring up a VM when your load is going to be high, and you can rapidly add this into the cluster and have more resources. So you don't have to start with a big cluster or a big machine. You can always start small and then scale up accordingly. That's the main advantage. So you're always utilizing maybe 80% of your resources. Sometimes. So when we talk about, let's say, VMs, what they give you is elasticity, as I said. You have a way of increasing and decreasing capacity as you go on, and adding or removing more machines. Is it the only factor that you need to scale your application? Can you right away bring up a new machine, add it to your cluster, and let it start working? No, right? What would you normally do? You'll have to get a VM with let's say, Ubuntu on it, or Arch Linux on it, CentOS on it, whatever. Now you'll have to install your application library, supporting dependencies and everything. So that's what is going to slow you down. That's where you need to install something on your machine and get your code working is that the code and the configuration is together. So let's say some code you wrote, let's say in case of a C code that you did, hash include stdio.h. We are all familiar with that. So what does it do? It uses the stdio system library. When you compile the C code, does it include the stdio.h file into it? Explicitly do it, but normally doesn't. So what happens is that there are certain system dependencies that are there for your code to run. So maybe the code you wrote might not work in a friend's laptop. Even worse if you have a different OS. So that's where containers come into the picture. You package your code and the dependencies together. Just think of it like a big binary. That's huge binary where your code is there, all the required dependencies, and let's think of it to the point of the operating system itself. So all these are packaged together. For example, if you see, normally if you have to run Postgres on your system, you install Postgres using a package manager or compile it from binary. Now, and then you run Postgres-d the data directory. So after that, if you are to do it the exact way using Docker, all you need to have is Docker installed. The only dependency that you have now is Docker or any other container management system. So there is Docker, there is Rocket. It's coming up now. They are still going through a rapid development. Docker is kind of stable. That's why we all talk about it. So Docker run. Let's say we have taken an example of a Postgres image from Asura/Postgres. That's all you need. Postgres is. Now, when you bring up a new machine and you want to add scale any of your application, if they are in the form of Docker images, it's very easy to do right there. You can right away bring up a VM with any machine, any OS with Docker installed, and start your application without thinking about anything else. No other installations are required. If you have 10 dependencies, you package it into one Docker image, and that's it. That machine only needs to have Docker. That's the convenience that Docker brings in. And packages. There come packages. There's new packaging coming up, which is called Ubuntu Snaps. Everybody does the same thing. They package your application and its dependencies. Now your code and the config of the machine that it needs to run are separate. Because this runs anywhere. It runs on your Mac, it runs on your Linux, it runs on Windows. It's kind of global. Now, the VMs that we talked about, when you need to provision a VM, these things are not special anymore. It can be any VM on any cloud provider, anywhere else in the world. So it's just one basic resource. We look at it as CPU plus RAM plus PC. That's it. So, but I'm not saying this solves the entire problems in the world. Like this, there are new problems that come into picture. Who is going to start these local containers? Who is going to make sure that all of these things are running? By the way, if you have any questions, feel free to stop. Any term that I say doesn't make sense, please feel free to stop. So now what happens is you need a way of looking at, let's say you have a cluster with 10 machines. You need to run one application on machine 1, another on machine 2, or you need to run 5 applications. Now, who is going to run? You don't have to. Typically, what would you do if you have 5 machines and you want to run 5 services? You will SSH into each machine. You will execute a watchdog command, systemctl, or something like that, and it will start running, right? So in similar thing you can do. Instead of the raw command for the process, and you can do Docker run. But when it comes to scaling things again, let's say you want to make something two copies, some 2 replicas you need to run. So what would you do? So you will have to go into each machine and then do it again. That alleviates the whole purpose of having this deploy anywhere kind of code, right? You will have to bring up a VM. Then again, if you tell me, okay, you need to go there and start typing Docker run, it doesn't make any sense, right? The entire point of me using Docker is that I don't have to go into the VM and do anything. If I have to do that, it's exactly the same as going into the VM and starting Postgres, right? So we use something like container orchestration tools. For example, there is Kubernetes, there is Docker Swarm, there is Mesos. So what these do is they see your entire VM, entire set of VMs as resources. Machines, each with 2 cores on it, it will see 20 cores. Similarly, it will see, let's say, 40 GB RAM. It will see 1 TB of hard disk. Now, when you tell one of its orchestration tools, okay, run this application, it will just figure out which machine have resource, which machine have space, which machine is idle, and it will just go and run the application there. All you need to give is the Docker image and some configuration values. So that's what all these container orchestration tools like Kubernetes or Mesos, all this. It lets you manage Docker containers. So it will also make sure these things are running, they are already healthy, all these things take care of. So that's about one part, containers. Second part is completely independent, but they're called microservices. So why would somebody use microservices? Any quick answers? So Ashwin mentioned about microservices. So he had a very specific use case. So something like that, anybody, this is why you should use microservices. Yeah, so continuous delivery, continuous integration.
Scaling.
Scaling. Okay, that's what I was looking for. So when your application is, let's say you have a monolithic application. Let's take a Django application. Anyone is familiar with Django? So when you have something like that, it really doesn't make sense to split that application into multiple microservices. Maybe you can split database and the application code. But if your application code itself is similar thing, it's better to have it in one place. Let's say your user management, your business logic. It sometimes makes sense to have them together if they are closely tied. So what I'm saying is, you don't use microservices just because you want scale. So you have your Django application. You want to support more users, you can always run 10 Python processes, 10 Django processes. Maybe 20, you can increase it depending on your resources available. Don't do microservices just for scale. This is what we have figured out after working with it for the past 4 to 5 years. So the microservices are an amazing tool, are an amazing way, as an amazing tool. When you wanna use multiple framework and multiple languages together in a single application, which needs to do the machine learning. Your business logic is in Java. Machine learning libraries are there for Java. What about with Python? You know how to write in Python. You already have a testing done. Now you want to write something in Python and run it along with your Java business logic. That's why you really should use microservices. Now, I'm not saying you can't really use microservices in simple applications. You can, but then your application need to make sense. So let's say your authentication, you can have it as separate microservices. But then your team should start thinking about each of the services as separate products. So your auth has to be a separate product. Your database or a business logic has to be a separate product. Your other business logic has to be a separate product. You need to version it as separate products. You need to handle the dependencies. What if your data API has some change? Your authentication service didn't know that. You updated data, but your auth is in a different version. Now this miscommunication happens, right? So you need to take care of all these issues when you start doing microservices. So use them only when it makes sense. One single huge use case could be when you need to use different languages together. That's the huge advantage of microservices. So another point,
different languages. I didn't get it.
Okay, so
because microservices are basically different stacks, right?
Yes.
Obviously, so different. So if I'm taking a microservice 1, 2, 3, okay, so one microservice will be on different stack. Different backend should be of different. So in that, how we can interact with multiple languages?
So by microservice, you mean a stack? What do you mean by stack? Your front end and back?
It's a stack of front end as well as back end. A language of front end.
Okay, that's not how we look at microservices. One microservice means, let's say your UI, web server which serves the UI. That's one microservice. Now you have another one which is the database. Now you have another microservice which handles user authentication and
kind of filled up.
Maybe not kind of LDAP. Basically the user module.
Yes, functionality will be
correct.
Divided into microservices.
Correct. Now let's say you have another module which does some data crunching. That's a different microservice. So microservice need not necessarily mean different stacks. There are different functional modules. Best language which is suited to do that work. You want to generate some PDF. You found a very good PDF, HTML to PDF generating library in Python. but your application code again is in Ruby. So you might want to use that Python library. Ruby from Python, you don't even want to go to that. So you make a Python microservice which has a HTTP API, JSON or RPG or whatever you want. The Ruby can call that API, generate some link for the PDF for the send it back to the front end. So then there should be another microservice which can manage all these things. Route request, there could be a load balancer. All these things can be done. So functional microservices. Don't split them because of their what do you say? You have 3 applications running, doesn't mean that you have 3 microservices. These are functional blocks.
I think you have the application request will be in case in this case.
Will be a request hopping, but that's one trade-off that you have. So
what would be the great advantage of microservices?
As I said, usability. So the great advantage is that you have the freedom of using whatever stack and whatever language is best for the job. You are not constrained of what is available in the current language ecosystem, the framework ecosystem that you are adopting. Let's say you start developing your application with Java. For you to need anything, there should be a Java library, right? Some external task that
Asking on a business perspective.
Okay.
Asking on a business perspective. You are telling on a development perspective. What I'm telling is on a business perspective, for example, take as Amazon. So if they are planning to go for microservices, what is the great advantage that they will see?
Point number 1, they are on a microservice. 2, so they need to have fast. Everything has to be quick. They have maybe Karthik.
Can I take an example?
I can take it.
Yeah.
So we go towards microservice architecture. There are a lot of use cases. One of the use cases which I would like to focus on is that, like when I'm like building on an application, there is a part of application which I want to do in a stealth mode. Like these are only specific for a bunch of users on the application. I can put it as a microservice, and it can run on its own. Just the routing, your entire front end needs to route to that particular application so that you can test that application. You don't have to integrate everything into your own application. It is a separate module on itself which can run on itself and can because respond to the user depending upon the needs.
So he's asking about it from a business point of view.
Can I take it up?
Yeah, of course.
I actually ported this microservice into production recently. It's a fintech application. I specifically went in for microservices mainly to address the concept of scalability. And the reason was I had a bunch of 3 microservices. I had 3 microservices hosted, and out of which only one microservice is to be scaled up or down based on the time, and other 2 can remain static. Okay, so this is one specific use case where microservice helped me a lot. So if I have to build a monolithic system and if I have to port the same thing, I can still achieve the same thing, same scalability. But what happens is I'll be having a C4 XLarge system which will get replicated again and again. But with microservices, a specific portion of that application which needs to scale up can be scaled up automatically with a minimal cost incurred in terms of the business value. So if I have to scale up, to give you a real-time example, let's say that we are building a banking application. So you are going to be faced with a lot of applications going to come into you. So let's say that you're going to receive some 200 million applications per day. Just a hypothetical scenario, okay? 200 million applications per day. But not all applications are going to get transformed into a loan for you. So is going to be a miniature system, but your application service is going to be a big system which is going to receive a lot of requests. So in this case, you need not have to scale up both your loan service as well as your application service, but you can scale up only that application service. So it's just an example that I'm giving.
Yeah. So I'll put a point like here, because in a decoupled environment, this is fine. But if you go on a coupled environment, for example, you take it as because we are, I'm in Verizon, that's the reason I'm telling. We are interacting multiple services. We are interacting multiple web services. For example, going to fetch for the address from the customer, and after coming back and finding out whether this customer is qualified for fiber or copper. And after that, we are serving the products to the customer. For example, you take this. This complete architecture, which is interacting with multiple services, which is tightly coupled, which is not loosely coupled. On this environment, on tightly coupled, what are the best opportunity that we can take it as microservices? You got it right. Microservice.
The way I used to think about microservices, at least the way I thought about microservices, the domain-driven.
Exactly.
So the moment you start bringing in the domain-driven design into your architecture, then you have a microservice that can be called within the bounded context. So when I say a bounded context, whatever it needs to do is readily available for it to do. Yeah, though you may be interacting with someone else or other, but the moment you start interacting with someone else or other, you have to be careful about the IOs, because each and every IO is going to be a blocking call for you. So your microservice performance will start degrading. So you have to think all these things before you get into designing a system into microservice architecture.
When we have decided what the basic idea that we got it from our mind is, because we are continuously deploying so many things for offers to the customers. If you take it as a provider of Vodafone, Airtel, the same way, the same job that we are doing. So continuously on daily basis, we are seeing multiple offers to the customers. So that is a microservice which needs to be deployed on daily basis, which is required. That part alone, as you have said, right, the functionality, that part alone we are doing as a microservice. That is one part. But on other area which I have said, right, so which is of tightly coupled. So I'm trying to pull up that area also as microservice. That's the reason I asked this question. Don't take it wrong. Thank you, guys.
Sure. I mean, functional decomposition is one of the primary principles of software design.
Yep.
If you're going to have a title, I can write the entire application in one class, in one public static void main, modularize them, encapsulate them, have unit testing. It's the same way. If you can split them off, and it makes sense to have them as separate individual processes, then yes, microservices is for you.
Yeah.
Else, microservices is going to hurt you really bad. It's not something that's meant for you. That's the word.
Thank you.
Just when you have some time, really let's make a 5-10 minutes left.
Yeah, sorry.
Yeah, sure. And we have time to chat during the lunchtime.
So, this is summarize that you have functional modules. Meaning you have to scale up each module separately. You can use microservices. And to integrate best of all the worlds, you can use microservices again. So now just wanted to conclude by having some opinionated approach that we use. So one thing is that let's say when we talk about all these independent services, one main concern is authentication. Let's say your application is going to have users. Now, how do you identify and authorize and authenticate the users? So for that, if each microservice is going to do that, it's again an overhead on each of the microservice authors, the developers, and that service itself. So what we have done is we have taken away authentication with the gateway. So what gateway does is it routes incoming requests to the service by resolving authentication at the same time. So when a user is logged in, a cookie is set or a token is set, and when you use the token or a cookie for the next request, he is correctly identified and authorized, and only then he is sent to the correct microservice. If he is not authorized to access the microservice, he is blocked right away. So that the authentication part is taken separately and tightly coupled with the the gateway calls the auth and check if the user is valid, and this is all done in very low latency using Redis and all. So that's one thing. And then another approach that we've taken is that everybody needs database. So we have created a bunch of data APIs. So we have used Postgres database, and over that we have built a JSON API using Haskell, and that will provide data APIs for every application. On top of it, these are very opinionated approach that we have taken, but you are free. So you are free to deploy any code that you want as separate microservices on the platform. So that will give you huge flexibility and huge. It will give you the entire open source world at your disposal. So again, microservices you have functional parts. You can scale them up, scale them down, add new nodes, any nodes. So that's about
one question.
most of it. Yeah.
So as part of the authentication, do you guys also take care of metering if it's required?
So at this point, we have not done that, but we eventually want to do that.
Because in an API world, most of the authentication happens via metering.
Yes.
Because it means, of course, that API key or the ID is one, but the fact that I still don't want to serve the customer, even if he's a valid customer, if he's crossed the limits.
Correct. Makes sense. Very well. Any other questions? So the initial failure, as we have said, you want to take a question? What are the failures you have faced on the way? As a company, while building microservices. While building microservices.
Challenges.
So I think one of the things is we adopted Docker
and
like,
Kubernetes.
So for instance, Kubernetes we adopted before version 1.0, right? So it was almost like the bleeding edge was literally bleeding edge for us because as we were writing code, there would be a version upgrade and it wasn't backwards compatible and things like that. So that was, I think, one of the, now it's become a lot more stable. We've sort of been through that journey. Even Docker, a lot of features that are available today, we adopted Docker almost, I think, 3 years ago, 2.5 years ago. Yeah. Yeah, so I think that was one of the things. The ecosystem was still evolving. They hadn't figured out a lot of these production issues. For instance, still some problems are unsolved in Docker, which we had to, like, for instance, I think the whole log rotation and that was using Dockers, right? So that part, so we have to write a lot of code which you would expect of a mature open source project. We've had to write a lot of that, and yeah, so there's a lot of firefighting that's been gone.
That's why we have put all this effort on top of it and have a unified interface for our clients and our architects. That we don't have to worry about all the technical difficulties or anything each time we do something without. And we have a layer over the Docker, Kubernetes, CoreOS, and which is deployed anywhere.
Yeah, so the idea is if there's a version upgrade for Kubernetes production, if you want to do it, there's several pieces that we do. So as a platform, then it becomes our responsibility to do that upgrade, push the upgrade when it's completely backwards compatible with the previous thing. So we handle the pipeline. We learned that by
You literally bleed. Okay, that's about it. I think there are 28 minutes. Sure. Thank you. Thank you so much.
See you guys. John here? Yeah. We have time.
That's inception.
So, do we go ahead with this presentation? Yes, no?
So we have a choice.
Okay, you guys wanted it. Okay, how many of you have used Ansible? Cool, I'll come to the right place. I'm a full stack developer. I don't know how to write shell scripts. That's why I learned Ansible. You'll know why. Okay. So, how do you guys deploy your web application or any application? Yes, Ashwin talked about a lot of blue boxes in his talk, right?
Hello,
how do you guys bring those blue boxes to life? You guys do it manually?
Chef.
Sorry?
Chef.
You're the chef guy, oh boy. I should be really careful. There is always going to be more servers you're going to handle in the future. You're not going to go less, right? You guys agree with me? Yeah. You basically don't have a choice. So why can't we just stick on with shell scripts? Life would be cool, right? Everybody knows it's the least common denominator, right? What is the problem?
Expressibility.
Expressibility. I mean, shell scripts are better at expressing things than Ansible.
Between imperative and declarative, I guess, because you'll have to tell
development time.
Exactly. That is the biggest thing.
No ID.
Both from a business perspective as well as a developer's perspective. You guys have tried this, okay? Your if doesn't work in Bash, and then you Google for like 3 hours. I've done that. I think many of you would relate this. Okay? And the problem is, I'll write it and it works perfectly on my machine, and then I go and deploy it, and then it will say that there's an error because the shell is CSH. Okay? Now I have to learn CSH. Okay, what does this line do? Those have written wrong ifs in Bash. That's my fear, don't worry. It's not visible, is it?
It would update the host file with the content.
Okay, so you write this in your shell script for your web application, you're deploying it. Okay? This is the 5th step, and then your 7th step fails. And then you fix it after 3 hours, you run that again. What will happen at this step? You'll have multiple entries in your host file, right? And the problem is, you never know this. Okay? So your host file has got as many number of duplicate lines as the number of times you run it. So this problem you have to solve. This is the Ansible equivalent of whatever you did, right? I don't include the font size. That's not going to help, man. I don't increase the size. So I'll just try to digress this. It's YAML basically. It's more human friendly than shell scripts, of course. Module called line-in file. Okay. In the etc host file, whatever matches this regex, you just replace it with this line. So there are a lot of things happening behind the scenes now. First, Ansible does not add this line blindly. If the line is already there, you just skip the step. So no more multiple entries. Yeah. For people who are very good in shell scripts, you can always do this. But don't try this at production. Okay. The other thing is you can run it parallelly. This is a script taken from a real life production scenario. Actually, I flicked it from servers or hackers website. So you can just read it, and can anybody take a stab at what this does?
Installs all those packages using apt.
Yeah, but
Only if it's in a Debian family.
yeah. So you can make it out, right? So we have this serial 25% remote user C round sudo yes blah blah blah. So the heartbleed vulnerability, right? So let's say that you're in charge of Flipkart's DevOps, and then they have a Flash Friday sale, and then you discover that there is a similar vulnerability right now. Shell scripts. You have to write them serially. There are 100 servers. You'll be fired.
Xargs.
Sorry?
Xargs.
I don't know shell scripts, man. That's a 1990. Okay. So this command can actually be run on parallel hosts. This line serial 25% makes sure that they are not updated all at once. Mitigate the vulnerability at a time simultaneously across all the 100 servers. You're still going to get fired even if you use Ansible. So it does it at 25%. So it takes 1/4 of the servers, updates them. You get the point, right? You can't do this in shell. There are a lot of workarounds that he will do in Index. I'm not as smart as it. the current state of tools, everybody does this. Puppet does, Jeff does, Ansible does. There is a new kid in the block called Salt. I don't know if anything is newer. If you guys know, please. Puppet, Jeff. Puppet basically uses Ruby as a DSL, right? Jeff?
Chef uses
I don't know. Ruby. What is the difference? Names? Okay. So Ansible does not use any programming language, any DSL. It's all declarative. Even guys like me can write code. What are the other advantages of Ansible? It is agentless, meaning you need not assume that you have to install something in your server to run it. You just need to have SSH, bare minimum. I mean, there's a case with Bash also. Bash has some problems. Chef do agentless?
Chef solo.
Solo does, right?
Solo does.
Yeah, somebody told me before the presentation. Okay. It uses YAML. I don't know why I put the rule of least providers. I forgot. And like I told, it's idempotent. I think most configuration management systems provide this feature. And instant gratification, meaning you can just get your server up and running in minutes. We discussed this parallel deployment. Well, we are at it. I don't want to eat up time. So let me rebuild the DigitalOcean droplet in a Devo meetup. This IP address is actually mapped to a domain called Duplex. It's my domain. I just want to illustrate how quickly we are able to build it using Ansible. Well, that is happening. Okay, there are some terms which you need to understand. I'll just quickly zip through it. Inventory is all the machines on which you run your provisioning scripts on. Your database server, your web server is an example of an inventory. So this is an example of an inventory file. If you guys are familiar with the Windows INI format, it's very similar to that. I think it is INI. So it can contain IP addresses, domain names, a lot of other things. So this is a tag which tags those servers. It batches them into, like, these are DB servers, these are web servers, and so on and so forth. Sometimes you provision missions using Ansible. You don't know the IP address or the domain name of that. You use something called a dynamic inventory. Most of the cloud providers, they inventory. You just indicate that you have to use this py file. A dynamic inventory can be in any language. It just spits out JSON, which is understood by Ansible. And when you provision a new machine, it gets added to the dynamic inventory. Let us say that you write a whole Ansible script to create a new EC2, I'm sorry, DigitalOcean instance, and deploy PHP or Django on that. So you don't know the IP address of that before. So that's the case where you use a dynamic inventory. A task is a single unit of work in Ansible. It could be as simple as installing a package. I mean, it's better advised that your task is as simple or as quick as possible. You should not do like 100 things. You just do one thing, and it should be predictable. We have this convention where we give a name to the task so that it's human readable. We can also have a task like service : name IP tables state equals stop without this part, but it sounds as ugly as a shell script, right? Nobody can read it and understand. A playbook is a bunch of tasks. So this is an example of a very simple playbook. All your Ansible YAML files start with a triple hyphen. It's a convention which indicates that it's a proper YAML file. And then you have to operate these tasks on these hosts, all meaning all the hosts in the host file, the inventories. So these are the tasks. I mean, they're fairly readable, right? You update the APT cache, you install Apache, you install MySQL, PHP. So there we install LAMP and like 4 steps.
From where the binaries will take?
Sorry?
If you give the installation, install something, where the binaries will take?
whatever machine you want to install it on. Like I have my I have Flipkart server, and I want to install LAMP stack on that machine, and then I just give Ansible posts.
Okay, in this previous slide, you haven't given the source code.
So
Source where it
Ansible
has to-
doesn't install packages. It uses the package
No,
manager to install.
like how you SSH into an Ubuntu machine and then install new packages. It does the same thing for you as a remote user, not on the same machine.
From repo.
It uses apt get install.
From repo.
Yeah.
From repo, you need to enable repo.
Okay.
His question.
Sorry.
So, right. No, he said the repo should be somewhere else, so it will be taken from there.
I didn't get your question.
You said install MySQL, okay? How the Ansible will identify where the MySQL?
Yeah.
I give you an Ubuntu machine. How do you install MySQL?
I haven't done that.
You should have done that before you asked the question.
Actually, instead of an apt-get, let's say we want to do it on a RHEL. So I want to do a YAML.
Yeah, you can instead of APT you'll have YAML. This is a module.
Yep, got it.
So
You can use the package from the repo.
Okay.
It installs.
Okay.
Okay. So I can understand your question. Where is the binaries, right? The source of the binaries. From this place, I am keeping the source.
Yes.
Take that source and go for installation.
Yes.
Okay, those two is gone actually. Everything you need to enable repo.
Okay.
So YAML module or APT, it pulls from the repo the packages and it goes for installation.
So what was his name? The chief guy.
Yeah.
Yeah. You're the chief guy. So, the thing is, he asked a question as to what if I have Red Hat or CentOS? I have to use YAML, right? So the point is, you have so many systems and so many softwares. You always have to end up writing a lot of if, else, and all that. So we have something called a role in Ansible, which is a set of specific tasks for a specific remote machine, which you can just include. It's just a module. Okay. So I'll have a role for installing Apache in RHEL. I'll have a role for installing Docker in, say, Windows or something like that. So roles, they're reusable. They work for a very specific use case. You won't write a role. Of course, you can technically write a role which will install Apache on any OS. You have to put a lot of if, else, and all that, and it's a hell to maintain. So people generally go for roles which are very specific, like install Apache or this version on this distribution. So that is an example of a role, and role can be redistributed. Meaning, you can upload your role in a place called Ansible Galaxy. Ansible folks hang out and distribute their modules. So you can put your role there. I mean, you can do it right away. Write a role and then you can upload it in Galaxy. Then people will start downloading it and using it, then reporting issues.
The problem is you'll end up having 5,000 different versions of Apache installation rules.
Exactly. But the thing is, whatever your pain in the butt is, then other people who have the same pain, they share your role and then improve. So this is an example.
Sorry to interrupt. How about installing it in a Windows box, or like it only supports?
No. If you are having Windows servers, Ansible supports Windows pretty well. If Windows supports anything via a script or a command, you can as well put it in Ansible. I'll show you a later snippet where you can, if you have existing shell scripts and you want to migrate away from them very badly, you can use Ansible to, you can go do it at a piecemeal way, like one script at a time. So this installs the LAMP stack. I showed you the task, right? It's a very, very diluted, watered, oversimplified version of a task. We have to do a lot of checks. So, so all those checks are done inside roles, and then I just have to call them here. So in this mission, I have to install web, MySQL, and WordPress. That's it. So these roles will be downloaded, and then they'll be installed. Let me just confirm that there's nothing in here. So this is the site. It's a Django application for which you'll give a URL. You'll convert it into an MP3 and then give it to you. There are a lot of free sites does it, but that's not the point. It's just a pedagogical application. Right now I have just cleaned up the server, so there'll be nothing here. Okay, script where we are doing the presentation. So that This will take some time. That's why I'm running it. No tricks or Ansible Galaxy is the command to scaffold new roles or download new roles from their servers. So this is how the structure of a role looks like. Everything is YAML in Ansible. So don't worry, you need not write any programming language whatsoever. Advanced syntax. Nothing big here. The thing is, let us say that you want to run your Apache web server in some other port. You can just go to that file and then change it by SSHing the machine, but that breaks the whole point of automation. So what you do is you have this concept called templates. Templates are nothing, just exact same configuration files with placeholders within double curly braces. These get substituted by Ansible variables which you declare in the YAML file. So for example, this is an example of a variable usage inside a YAML file. This previous one was an example of variable usage inside a template file.
What will be the replace?
I'll show you. So you have a different domain name here, right? For your application, it might be the same as what I have, right? So you'll just give domain equals or domain colon from www.example.com when you're running Ansible in the playbook.
That will be different from the host file.
Yeah, whatever you declare. So you have a variables file, and then you have a lot of placeholders. Ansible just substitutes it where whatever name it finds. So we have a domain called Drupal test. So wherever you see the domain variable, Ansible will substitute it. So this is how you use a template. So this is it ends with the .j2, which is an abbreviation for Jinja. Jinja is a templating language. I don't know.
It's a Python based.
So yeah, so it takes this template file. So when you specify template, Ansible automatically takes all the placeholders inside this file and then puts it here. So you can see that even the file name is template text. Okay, I'm just giving examples which capture all the use cases. You can even give conditions like these. These can be simple expressions, and even complex ones. So do this if I have one of these SSNs. We can have multiple number of expressions. So the problem is whatever declarative language you enter, you always have to write some kind of business logic, which this and that. That is why we have these conditions. A lot of people argue that you could as well use shell scripts here. But the thing is, we don't need anything more than. So why should we again reinvent shell scripts? They made a wise choice not to do that. So this colon is actually the name of the module. Ansible actually contains hundreds of core modules. There are some modules that are available for download. You can write modules in any language, so most of them are written in Python. An EC2 module with these parameters. So this will create and launch an EC2 instance from this region, key name, instance type, image, etc. These can be variables in some other file or the same file. Ansible will do that for you.
One doubt.
Yeah.
So it is under ELB, okay. I'm running 3 instances in ELB. So is it possible to then again I can post in
You won't enter into the instance setup. You will do everything from your shell.
That's okay. So I need to restart the server.
Yeah, you can do that, right? You can give a command to restart this particular instance.
But I need to take from ELB. I understood my question. So it's running in ELB. So I don't want to down in even one instance. Okay. So what I will do is I will manually take it from the ELB. Then I will restart. Then I will push in.
Yeah, you can write a task for that.
These are basically configuration tool. For your requirement, you can use that predefined modules, or if you don't find any modules as per your business requirement, you can write your own script and you can use the model called execute, and you give the script name there. Okay. So predefined models are there. Okay, Ansible is good. They are probably very good recommendation. Okay, you use that all the modules. If you don't find any suitable modules, okay, you can write your own logic via the script. That script can be called in the Ansible script.
Only requirement there is that if you are able to remove that
CLI,
if you can do the same activity through CLI, command line interface, then you can do the same thing to Ansible also.
No, I'm doing in Amazon.
Correct. Amazon CLI is what I am talking about.
Yeah.
So if you can be able to log into Amazon CLI, and if you are able to remove an entry from your ELT, you will be able to do the same thing for Amazon.
I'm not using command line. That's what I'm doing.
But how to use?
Discuss what Ansible Galaxy is. You guys can check it out. There are a lot of roles there. You can just do some window shopping and find your favorite role. So we already ran the script. This is how typical Ansible provisioning output looks like. So yes. Okay, so this playbook is a collection of tasks. It is to provision a YouTube ADL DB server. Okay, so if you open my if you see around Ansible playbook site.yaml, site.yaml just contains these two includes. One is for the DB server, and the other one is for the web server. So if you open DB servers, so I've used a variable there. It provisions an application name DB server. So it uses these roles. This code is available online. You guys can check it out. So it uses some variable files. This is a variable file. No if, no else, no functions, nothing. Just simple lines, YAML lines. It reads these YAML files and then it passes it and then it runs these tasks. So it skips a task if it finds that this is not relevant to this target mission. And then it prints this brown color changed if the state of the system has changed. Which, remember, Ansible is idempotent. Sometimes it says OK in green. It means that the state of the system has not changed. And of course, like all systems, the errors are in red. A lot of errors this one. We'll show you. It'll take another 5 minutes. I have a few backup slides. Ansible Tower is the commercial version of Ansible with all the fancy pants UI and all that. You can test roles in a lot of ways. There is something called a kitchen. It is agnostic of whatever provisioner you're using. You can even test it with Jeff. Kitchen actually gives you the provisioner type and the script you want to run. Provisioner can be backend or explosion or EC2. And then the script can be whatever script you're running. And then you can write down a local backend box. If it works, you can push the script. And Ansible provisions your code to almost all the popular clouds, even clouds like OpenStack, all that. The most important thing is your whole infrastructure is now as code. You can version control it, you can branch it off, you can check it along with your source code, and anybody in your organization can run that and then get the same results. The bridge between developers and ops admin people is closing down. ops team. Your developers, I'm sure they can learn YAML, they can learn Scala. So no need of a separate ops team. You guys can deploy it on your own if you know Ansible. If you're having a lot of legacy shell scripts, it's very easy to move to Ansible on a piecemeal basis. Ansible has got the shell module where you can run the shell script, capture the output, give it parameters and all that stuff. That was the question you asked, right? So, any other questions? We can wait till it deploys or we can go for lunch. I can even show it off. Yeah.
For authentication, we will keep it for logging and access of your service. So I have 4 instances. So
yeah, it works via SSH. It's a very simple protocol. It is available for every cloud machine. So you just need SSH access to your machine. If you don't have SSH access, then you cannot use Ansible.
Each server have own access. A key file means it's possible, right?
Yep. So for whatever server you want to deploy or run an Ansible script, you need to have SSH access to that server. It may not be the root user.
Any user, of course.
Yeah. So whatever privileges that user has on the remote system, he can run those via Ansible.
Yeah, of course. We haven't run the Ansible project because it is a passwordless user, right, for a remote system.
Yeah, that's what SSH. That's the whole point of SSH, right?
No, without that. See, because passwordless.
There is a provision in Ansible called Vault, where a lot of times you want to put sensible data. It can encrypt that and then check it in so that you can use it.
Vault is available as a playbook or
Ansible. Yes. Open a Vault encrypted file, you just see random numbers.
Sure. We have lack of time. Can we see the demo afterwards?
Sure, no problem.
Karan continue his presentation.
Yeah, yeah.
2 o'clock we need to close the
Right.
file.
So 2:30 they will close live.
Sure, sure, no. Yeah, no issues. Should I cut the call?
Yeah.
Thanks, guys.